In this lecture, we're going to take a look at the stress state from torsion, and then we're going to take a look at torsion of systems. Now, what I mean by the stress state from torsion, we know already that we can calculate the shearing stress anywhere on the cross-section of a bar when we apply a torque to it, and that the maximum shearing stress occurs on the outside diameter. We can find that by torque times the diameter over 2 divided by the polar moment of inertia. And in this case, if I have my round bar, if I'm applying the the torques this way, then I get what's known as a state of stress on the outside of the bar. I'm going to show this on a little square called a stress element or a stress block. And we know previously that shearing stresses always act as a set. So I have a shearing stress coming down this way and a shearing stress coming up at the back. Notice that the arrow that the shearing stress is pointing is determined by the direction of the torque on that respective side. And on the left side, the torque arrow is curling up this way, so the shearing stress arrow is going up. On the right side, the torque arrow is curling the other way, going down across the side that we see, so the shearing stress goes down. To keep this in equilibrium, we also need shearing stresses in the horizontal direction. And all of those stresses have the same value. It's the same stress. It's the maximum stress on the outside edge, the torque times the diameter over 2, divided by the polar moment of inertia. Now, like we did with bars and tension, we took a look at stresses on an inclined plane. We can also take a look at stresses on an inclined plane in torsion. Our approach is going to be slightly different than what we did when we looked at a bar in tension, where we physically slice the bar in half. Here we're going to take a look at this square that I've just drawn, and we're going to find equilibrium of this little square. So let me draw this kind of big. But here is my stress block or my stress element, just as I have it on this picture. Where I have these shearing stresses. I'm just going to label these shearing stresses tau. All right. So I want the stresses at an angle. Let me change colors. And imagine there's an angle running through this block. And it could change. It could be 0 degrees where this red line is straight up on the left. It could be 90 degrees where it's straight across on the top. But we're going to use the notation that the book uses. They call this angle from the vertical to that slant the angle theta. We want to find out what the stresses are on this red slant. And let me switch back to blue. We can think of this in two ways. We can draw this triangle that we have right here on a side view, or we can think of it like in a 3D perspective type of view. And I'll just dot in the hidden lines in here. All right, so the angle theta is here, and it is here in this picture. We have our shearing stresses, and I'm going to draw those on my little triangle. And those are the values tau. And what we want are the stresses on what are called the inclined plane. So we want the stress that points off in this direction. I'm going to call that sigma n in the n direction. And the t direction is a shearing stress that our book likes to call tau nt. Now, we can't do the summation of stresses equal to 0. That is not a thing. But we can do the summation of forces equal to 0 if we have equilibrium. And so we're going to convert these stresses into forces by multiplying them on the areas on which each of these different stresses act. All right, so what do I mean by that? Let's look at this little red line here. The distance from the left edge of this to the red line, I'm going to call that distance S2. The distance this way, I'm going to call S1. And over on this picture, there's S1 and S2. And here's the thickness of the little wedge that I have. I'll call that dimension T. The area of the bottom is going to be S2 times T. The area of the side is going to be S1 times T. And the area of this inclined plane, if we call that dimension L, I'll call that area of the inclined plane, or A, is equal to L times T. If we know the angle that we're looking at, the angle theta, we can find out the dimension S1 in terms of the angle theta and that slant length L. So the sine of theta would be equal to S2 over L. The cosine of theta would be equal to S1 over L. So L would be equal to S2 divided by sine theta, or S1 divided by cosine theta. Well, actually, what I want to do is I want to find S1 and S2 in terms of L. Let me erase these. I want to write it this way. S2 is equal to L sine theta, and S1 is equal to L cosine theta. So I can rewrite that in here as T times L times the cosine of theta, and this is T times L times the sine of theta. Of course, T times L is the area of the inclined plane, so this is the area times the cosine of theta, and this is the area times the sine of theta. So now that I know what those areas are in terms of the inclined plane area, I can construct a diagram that'll show me what my forces are on that wedge or that little block. So I'm going to redraw this picture, but instead of stresses, I'm going to put forces on it. All right, so I rearrange this a little bit, and now I want to take a look at the forces on that wedge. All right, so the area of the inclined plane was A, so the force would be sigma n times A. I'm going to call that Fn, and this force Fs would be equal to the shearing stress times A. Now on the bottom there's a shearing stress tau, the torque times diameter over 2 divided by the polar moment of inertia. If I take and multiply that by the area times the sine of theta, I'll get a force in the x direction. And over here, I'll get a force in the y direction if I take that shearing stress and multiply it by the area A times the cosine of theta. All right, so we use this information over here. Let me make a little bit of room by getting rid of that now. What we're going to do next is apply our equilibrium equations. We're going to do the summation of forces in the n and the t directions. We could do the x and the y directions if we wanted to, but to make things, what we want sigma n and tau and t. To make those easier to solve for, we're going to do the summation of forces in the n and t directions. Now before I do that, we need to break these forces up into components. One component here in the t direction and another component in the n direction. And if we do the geometry, we're going to need to figure out what the angle theta is in this picture. Okay, likewise, we're going to break this force up into the n and the t direction. Now in this picture, this would be the angle theta that I have right here. Now, if you can't see that, then what we can do is we can construct a diagram. Let's do that over to the side. I'll try to draw as straight lines as I can. The angle that the wedge makes is off the vertical, so this is the angle theta in this picture. Now we have a force that's going horizontal, but we want to break it up into components that are in the N and the T direction. Okay, so this is the N direction, and this is the T direction. All right, so there's a right angle between the dotted line and the solid line right here. So this is 90 degrees minus theta. And so that means in this picture, this angle would be the angle theta. So that should be this one down in the bottom. In a similar way, you can find the angle theta for this picture as well. All right, so if we do the summation of forces in the N direction, we have sigma N times A plus the component of this force, tau A cosine theta is the force, and we want the sine theta component. Okay, and in this picture, plus the force, tau A sine theta, and we want the cosine theta component equal to 0. If we do the summation of forces in the T direction, we will have tau in T times A plus the force tau A cosine theta, and that is the cosine theta component. And then in the negative T direction, we'd have tau A sine theta and the sine theta component equal to 0 for equilibrium. So what we're going to do is just simplify these a little bit. We'll notice that the A cancels out in both of these expressions when we set it equal to 0. So sigma N is going to be equal to minus 2 tau sine theta cosine theta. And if we do a trig substitution, we can write this as minus tau sine 2 theta. And tau nt is equal to, we got, bring these to the other side, we have a minus tau cosine squared theta plus a tau sine squared theta. And we're going to rewrite that then. If we factor out a tau, we're going to have sine squared theta minus cosine squared theta. We can rewrite that as minus tau cosine 2 theta. All right, so now the important thing here is not these equations. It's what we did to get to these equations. So I don't want you to memorize these equations. They're very specific. You have to have a state of pure shear, and you have to define theta just exactly as we have done here. We need to get these equations because we need to talk about them, but I don't want you to memorize them. So I'm just going to put a little note here, don't memorize. It's better to understand the process that we just went through. And you'll have some homework problems where you have to use the equilibrium method to find the stresses. All right, so let's take a look at these equations for a moment. Suppose we wanted to find the maximum shearing stress in a bar that's subjected to torsion. So here we have our bar. And we have our torque applied to it. And we want to find the angle, theta, as we've defined it here, where we have the biggest shearing stress. Well, to maximize these equations, we could take a derivative, but I think you can see when theta is equal to 0, the cosine of 0 is 1. When theta is equal to 90 degrees, we have 2 times 90 degrees. The cosine of that, 180, would be equal to minus 1. So the maximum shearing stress is at a 0-degree angle. All right, so let's label this item 1, 0-degree case. The state of stress looks like this picture that I'm going to draw, where we have just shearing stresses. When we put in 0 degrees, the sign of 0 is 0. We don't have any sigma. If I wanted to see what this would look like when it was distorted, then my strains would cause it to take a shape like this. And I'm exaggerating this so we can visualize the deformation, but we can calculate the shearing strains if we wanted to. The shearing strain would be this angle in this picture, and gamma would be equal to the value of tau divided by g. Now in this picture, tau is the maximum shearing stress on the outside diameter, so it's the torque times diameter over 2 divided by the polar moment of inertia. We saw in a bar in tension that a 45-degree angle was kind of special. It gave us the maximum shearing stress in the material. So let's take a look at a 45-degree case for a bar in torsion. At 45 degrees, that means our square is oriented like this. That's kind of a sad-looking square, but that's okay. All right. So at 45 degrees, the cosine of 90 degrees is 0. We do not get any shearing stress on any of these surfaces of this block. When I go to positive 45 degrees, multiply it by 2, that's 90. The sine of 90 is 1. The negative sign here, what I get is a normal stress that points inward on the faces of this block. And this would be the sigma at 45 degrees. Now the value of that happens to be the same number as tau, which is torque times the diameter over 2, divided by the polar moment of inertia. If I go minus 45 degrees, the sine of minus 90 is minus 1, so I have tension in these two directions. Let's see, I need to put a minus sign here. Well, I'm putting the magnitude, so I don't need that. I have to be a little bit careful here. Since I drew the arrows in, I don't need the minus sign. But at minus 45 degrees, the magnitude is also tau. Torque times the diameter over 2 divided by the polar moment of inertia. And these are the maximum normal stresses for a bar in torsion. So let's write this down. The maximum normal stresses for a bar in torsion is at 45 degrees. If I wanted to calculate the strains in that square, and that's supposed to be a square shape, what we're going to see is that it's going to stretch out in certain directions. It's going to get shorter in the others. So it's going to turn into a rectangle that looks like this. And if we think of this as the N and the T directions, we can calculate the strains in the N and the T directions by using 3D Hooke's law. Where this is sigma N and this one is sigma T. All right, and then likewise, sigma T over E minus nu sigma N over E. All right, so these strains will have opposite signs, but they'll be calculated in a similar way. The strain in the Z direction coming out of the page would be 0. All right, so one of your homework problems will just be simply to make these sketches and calculate the strains. In each case, the value of the stress at 0 and 45 degrees is the same number, torque times the diameter over 2 divided by the polar moment of inertia, but its meaning is different. At 0 degrees, it's a shearing stress, and at 45 degrees, that number is tensile and compressive normal stresses. Now we can use this fact that we get normal stresses even when we put a torque on a bar to help us figure out material behavior. And in a lot of books, and I don't have the picture to show you here, you can take a look at brittle and ductile materials and see how they behave in torsion. If you have a ductile material, the failure surface for a bar in torsion will be clean across the cross section. Ductile materials tend to fail because of high shearing stresses. So they're getting sliced in half due to this shearing stress arrow and this shearing stress arrow. If you have a brittle material, the tensile stresses are important, and they'll tend to fail along a 45-degree helix. I don't know if I can draw that, but let me give it a shot. So you will see pictures of brittle materials like cast iron fail at a 45-degree angle because the normal stresses are the highest. All right, so if you get a chance, take a look at some pictures of that. Now, our last topic for this lecture is the torsion of systems. And so what I mean by that is if we have a couple of bars attached to each other, you can figure out the total angle of twist at the end of the structure. I'm just going to make up some numbers. Maybe this is 1,000 Newton meters. And going this way, maybe this is 5,000 Newton meters. Element 1 and element 2. Now we know our general formula for the angle of twist is an integral along the length of the bar of t over I sub p g dx. And it's very similar to what we saw for the deformation for a bar in tension, where we had an integral along the length of the bar of f over ae dx. And in fact, these are very analogous. Just like we have positive and negative signs for the deformation E, we can have positive and negative signs for the angular deformation phi. If we have a system of bars like this, the total deformation for materials in series would be equal to the addition of the individual deformations, so phi 1 plus phi 2. Now, if you have a constant force, material properties, and cross-section, then this integral becomes pretty easy. Likewise, in tension problems, if we had a constant force, cross-sectional properties, and material properties, then we have an integral of dx. And so in this case, our formula is TL over I sub PG, and in this case, little e is equal to FL over AE. These are two important formulas that you really ought to know. So when we talk about torsion of systems, to calculate the total angle of twist at the end, and this would be in radians, we would go TL over I sub PG for section number 1 plus TL over I sub PG for section number 2. If we know the diameters and we know the material properties and we know the lengths of the bars, the only thing really left to find is the torques. We do these through free body diagrams. If I want the torque in section number 2, I would make a cut inside section number 2 and sketch out the free body diagram. Here's my applied torque. If I use my right hand rule, then I would have a double-headed torque arrow going this way to represent that torque of 1,000 Newton meters. And to keep this in equilibrium, then I would have also 1,000 Newton meters going in that direction. That would be my torque T2. If I make a cut inside section number 1, drawing this flat, here's my 1,000 Newton meter applied load. Here's my 5,000 Newton meters. Now this goes in the opposite direction. Here's my torque T1. If I do the summation of torques down the x-axis, I have minus T1 minus 5,000 plus 1,000 is equal to 0. As I have it drawn there, my T1 would be equal to minus 4,000 Newton meters. The negative sign on the torque means it really points the opposite direction from what I have assumed. The double-headed arrow would point to the right. But that's okay. I can leave it as I have in that picture and just know that that T1 is minus 4,000. To put this into my deformation equation, I would take that sign and just bring it right in. I have minus 4,000 Newton meters times the length of bar 1 divided by I sub P1 and G1 plus T2, which is 1,000 Newton meters times L2 over I sub P2 G2. All right. Now, we've done a lot of these kind of problems previously, and I want to emphasize that the units on this will end up being in radians. But I'm not going to go ahead and put in numbers. I'll let you put in your own numbers so you can calculate your own angle of twist. So one last concept that we need to talk about before we go, and that is torsional stiffness of a system. There we go. All right, so torsional stiffness. Before we get into torsional stiffness, let's just review what stiffness of a spring is. If I have a spring and I apply some force to it and I measure some displacement, if it's a linear spring, we say that that spring has a stiffness that can be determined by rearranging the formula F is equal to Kx, or delta X. And we say that that K is the stiffness. If we look at this expression, on the left-hand side we have a load term, and on the right-hand side we have a displacement or a deformation term. In the same way, when we talk about stiffness of a single bar in torsion, the deformation of the bar is given by phi is equal to TL over I sub PG if it has a constant cross-section and all that business. If I rearrange this formula so that I have it look like F is equal to Kx, well, let's see. I would have T is equal to I sub PG divided by L times phi. Now I have a load is equal to some coefficient times some deformation. This term right here is the torsional stiffness of a single bar. All right. Now, in other cases, we may have more than one bar attached to each other. So we have a system or an assembly of bars. But I still want to apply just a torque at the end. And I know I'm going to get an angle of twist at the end. We'll call this element 1 and element 2. I don't have any other intermediate loads, just a torque at the end and an angle of twist at the end. We may be interested in evaluating what the torsional stiffness is of this assembly. We want an equation that's very similar to what we just wrote, but we want the torque at the end is equal to something times the angle of twist at the end. Well, in order to get the twist at the end, this is materials in series, statically determinate. We just talked about this. We have TL over I sub PG for each section. There we go. And if we do a free body cut in each section, both torque 1 and torque 2 are equal to the torque at the end. Again, with a single load applied to it. So that factor is in common, so I'm going to factor that out. And we're really close. We have deformation is equal to some coefficient times the torque at the end, but we want to rearrange this so that we have the torque at the end is equal to some coefficient times the deformation at the end. So we have the reciprocal of that term from the previous expression. And this whole thing in the bracket is the torsional stiffness of the system. Now, if you have 3 bars, you'd have an added term down on the bottom. And so we can construct the torsional stiffness of however many bars that we have. The key is that we have a torque at the end and a and an angle at the end. Now you can do a test in a lab where you can measure the torque and you can measure the angle of twist on a structure, and you can divide those two numbers and you can get your torsional stiffness that way. Okay, so it'd be something like Newton meters per radian. It's a very useful concept. When I worked at General Motors, we would test the front end of a structure for its stiffness, in tension, and in torsion. And if we did any structural modifications to it, we could either numerically or in the lab test to see what the new stiffness was, to see if we were headed in the right direction. If we wanted to make a stiffer front end structure, then we would increase the sizes of the cross-section members, cross members or so forth, and then we can tell whether or not our design was having the effect that we wanted it to. All right, so that'll wrap up this lecture on stress state from torsion and torsion of assemblies.